Look at these rocks. Look at them. Look at these rocks. These rocks. Look at this rock. Look at this guy with this. Look at that mustache. Look at this guy with this mustache holding this rock. Why am I showing you these rocks? What we're looking at is this right here in his hand. This is referred to as the Cullinan diamond. The Cullinan diamond was the largest diamond ever found. It was humongous in relative terms. It was found in 1900 something, 5, something like that, in the Cullinan mine by some underpaid workers, I assume. They showed the rock to their boss. That's this guy pictured here. And then they established the fact that this was, in fact, a huge, rough diamond, which could potentially be worth a fortune. So the story of what they did next is actually kind of interesting. They took this rock, they made a replica of the rock, and they transported the replica with armed guards over to the UK from Africa, where it was found. And they very carefully guarded this fake, sort of draw attention away from it, so that most people who were watching would assume that this heavily guarded rock was the real thing, when in fact the real diamond was just shipped in the mail in a little biscuit tin, and then safely somehow managed to get to the right hands. And so then this rough diamond was cut up into these 9 stones that you see here. And then they were cut into precise gems, and many of them are part of the crown jewels today. It's estimated that the largest rock, which became, I forget which part of this set, but the largest rock would be worth about $400 million today. So why am I talking about diamonds? Well, what are diamonds made from? They're entirely made out of one element, just one element. Can you guess what that element is? It's carbon. Carbon is the one sole element that makes up the diamonds. And so today's lesson is all about how carbon moves through ecosystems. But I wanted to start here with diamonds because people are kind of obsessed with this stuff. And I think it's sort of an interesting parallel that some of the two things that people tend to obsess over are diamonds and, of course, fossil fuels. Coal being one of the main fossil fuels. Coal is defined as having at least 50% carbon. So we already know that carbon is important for living things. You guys already know that carbon makes up the backbone of DNA, the sugar phosphate backbone, lots of carbon in those sugars. And so we know that carbon can be found in all of the molecules of life. All organic compounds have carbon in them, so it's essential for living things. We've established that. And today what we're going to hone in on is how the carbon found in living things, how the organic carbon compounds move through ecosystems with a process called carbon flux. And so the title of today's lesson is going to be carbon cycling. Carbon cycling. This is how carbon moves through ecosystems. Here we go. So, some terminology just to get us going. If we think about carbon present in ecosystems or in the whole biosphere of the Earth, we have to discuss what are called carbon sinks and carbon sources. And this is some vocab. So if you're taking notes, here we go. Carbon sinks are any areas where large amounts of carbon can be stored. Maybe temporarily, but it is stored there. An example of a carbon sink would be the atmosphere. The atmosphere can hold a lot of carbon in the form of either methane or mostly as CO2 up in the atmosphere. Now, another sink would be if we were to add up all of the terrestrial organisms, which, of course, start with primary production. Moving photosynthesis, primary production moves that inorganic CO2 into the producers, which then moves through all of our trophic levels and become part of our organic materials and our terrestrial organisms. That's another sink. One other sink would be the actual ocean. The water in the ocean is a huge carbon sink. The ocean can absorb a ton of carbon in the form of CO2 and also calcium carbonate. We'll come back to that in a second. And then, of course, fossil fuels are a giant carbon sink. We have a lot of carbon stored as old organic material, which has been converted into things like oil and coal and peat and lignite, things we'll talk about later. But fossil fuels are another huge carbon sink. Now, that's a carbon sink. A carbon source is any source where the carbon is being moved. So you can think of photosynthesis as a source, moving the carbon from one sink to another. You can think of combustion, burning things, as another source of moving carbon from one sink to another. And so you've heard of the carbon cycle, and I don't want to bore you with stuff you learned when you were 10 years old. So we'll start with some of the less obvious examples. We're going to start with how carbon is cycled through aquatic ecosystems, which is really important when it comes to the topic of climate change. So carbon flux or carbon cycling in aquatic ecosystems. Here we go. So the first thing you need to know about the way carbon moves through aquatic ecosystems is that water can absorb a certain amount of carbon dioxide. So a lot of the carbon dioxide from the atmosphere can actually just diffuse. This little red arrow here shows carbon dioxide diffusing into the oceans, and the ocean can dissolve that CO2. Now, only so much CO2 can be dissolved, and then as we start to get an excess of CO2, it will then just diffuse back out. And then while the CO2, while this carbon dioxide is dissolved in water, it can react with water molecules to form a compound called carbonic acid right here. This is a substance you should be familiar with moving forward. And carbonic acid, as the name states, is an acid which then can alter the pH of the water. So this carbonic acid is present when a lot of CO2 is dissolved into a body of water. And that's okay in small amounts. What we're seeing right now across the globe is that the CO2 levels are so high in the oceans that the oceans are becoming slightly more acidic than they used to be. Now, keep in mind that the ocean is actually alkaline, it's basic. pH is not neutral in ocean water. So when we say that the ocean is becoming acidic, when we say ocean acidification is occurring, what we mean is it's becoming less basic. So it's getting closer to neutral, but it's not technically acidic yet. And the reason it's becoming more acidic is because of all this carbonic acid that forms as CO2 is dissolved in the water. Okay, so that's one way that carbon is held in water, is dissolved CO2 and carbonic acid. Now that dissolved CO2 is accessible by any organism living in the water that can conduct photosynthesis. The most important photosynthesizing organisms on the planet are not trees, as you might think. In fact, most of our oxygen, at least half of our oxygen that we breathe comes from little microorganisms in the ocean, referred to as cyanobacteria. And so these are photosynthesizing bacteria. And what do they do? Well, because through photosynthesis, they're going to take CO2 and water. They're going to conduct photosynthesis using energy from the sun, and they'll produce oxygen as a waste product. That oxygen builds up in the water, and then eventually, if the concentration's high enough, it diffuses out into the atmosphere, and then we get to breathe that. And so we get about half of our oxygen from these guys. So every other breath that you take, well, you should thank the cyanobacteria for that breath. So then this is how primary production can occur. Any aquatic photosynthetic organism could potentially do photosynthesis. It would be starting our primary production, right? So cyanobacteria or aquatic plants is primary production occurring in aquatic ecosystems. Now, then we move on with a flow of energy and flow of carbon. Well, these cyanobacteria are made of organic carbon compounds, and they could be gobbled up by some little microscopic animals. We call these zooplankton or zooplankton. Plankton refers to teeny tiny little free-floating creatures. They're not always teeny tiny, but the point is that they drift on the currents. They're not very good at swimming, so these are tiny little guys, zooplankton, which then eat the cyanobacteria, And now the carbon, the organic material, the food that was in the cyanobacteria, is now ingested by these zooplankton. And so now we have a flow of carbon by feeding into these guys. And then, of course, tiny little fish can munch on them, and now the carbon flows into the little fish. Bigger fish will eat the smaller fish, and then through feeding, the carbon can flow through those trophic levels throughout this ecosystem. Now, another way that carbon flows or is stored in the oceans or in aquatic ecosystems is this compound called calcium carbonate. It's right there in the name, carbonate. Calcium carbonate. The calcium carbonate is a substance that's found in many shells. So little tiny snails or mollusks will make shells to protect them, and those shells are the things that we find washed up on the beach. So you'll find little animals who build these calcium carbonate shells as protection, and then when they die, the shells remain, and there's lots of carbon, calcium of course, but carbon stored in those shells, and that carbon can then become fossilized, and we get these huge beds of fossilized carbon in the form of calcium carbonate. In fact, limestone, which makes up the bedrock of Florida, is almost entirely made out of this stuff. So it's a pretty important sink for carbon. Here's another random picture of a fossilized shell. There you go. Okay, next, this is an entirely different process. We're shifting away from the oceans to a detailed, perhaps a bit nuanced method of carbon flux. I'm skipping over the more obvious stuff for now. This is a process called methanogenesis. And the word genesis refers to the creation of something, right? And so this is the creation of methane, methanogenesis. What we're looking at here is a couple of people digging up little flammable patties of peat. We'll come back to this stuff called peat in just a second. So methanogenesis takes place in areas like this. See this little body of water here, or regions like this are called bogs. And so in a bog, what you have is soil. Underneath this grass, you'll have some soil, which is waterlogged, meaning it's completely soaked in water, which you might think is a good thing. Plants need water, and there's water, yay. But no, there's so much water that remains in this area that it's flooded, and the plants are drowned because they can't exchange gases. So the plants can't live here. So it's a dead zone where this bog is located, this waterlogged soil, and this water becomes very acidic over time. And so these are the conditions that are required for methanogenesis. 1, the soil must be waterlogged. 2, the soil must be, or the water, must be acidic. So in acidic, anaerobic environments, meaning there's no oxygen, but you have water instead. So anaerobic, acidic environments like this bog, waterlogged soil, gives you the right conditions for what's called methanogenesis, for the creation of methane. Now, the way this works is that deep inside of this bog, you have specialized prokaryotic organisms called archaea. You've heard of archaea. They're prokaryotic, so they're similar to bacteria with some important little biochemical differences. And so these archaea are adapted to survive in very harsh environments like this bog, where basically not much else can live. And they conduct anaerobic respiration in the bottom of this bog, and they slowly break down all of the carbon compounds in this anaerobic environment. So the grasses fall in here, and it causes a slow breakdown of organic material, and you get a high concentration of carbon as a result, and they release methane gas as a byproduct, hence methanogenesis. Now, in areas where this is taking place in large areas, cool sentence, you're going to get a ton of methane building up in this muck. So what you can do is you can take your hoe or your axe or your shovel or whatever you've got handy, and you can chop into this stuff. And when you break it out, it's packed with carbon compounds, methane especially, which is flammable. And so you can actually burn this stuff. And so what people do is they go to this place called a peat bog, and they chop up this muck, which is referred to as peat. That's P-E-A-T, not like peat, P-E-T-E, that's the name, but P-E-A-T can be chopped up into these little bricks, and you can burn this stuff. And this can be used as a fuel source. Of course, it's not a very safe fuel source because that methane combustion releases some toxic gases. So you have to make sure that you have the right equipment if you're going to do that, which clearly these people do. They know what they're doing. So they've got their methane chopped from the bog. They're going to toss it in their little buggy and take off and go burn some stuff and make some stew. So methanogenesis is important for carbon flow or carbon flux, because what this does is it allows for the sequestration or the entrapment of carbon. This is like the first step. Now, if you take this peat and then you just let it sit there buried for very long periods of time, we can then get that peat to transform into more useful, more predictable substances like lignite or coal. And so what happens is, like, imagine you have a large swamp like this, and the swamp will be, soaked with water. So these anaerobic acidic waterways where peat formation is going to occur. All this organic material dies and falls into the water repeatedly, and we get a whole bunch of organic gunk building up down here. This gives us peat. Now, over time, we have lots of geologic changes. We're talking about hundreds of thousands or millions of years here, at the very least, where we have geologic changes, sea levels rise and fall, more soil moves in or out, the bog could dry up and then get covered up again. And so over time, through lots of changes to this environment, this peat then gets buried underground, and over time, that buried peat gets exposed to more pressure and more heat, and that converts the peat into more pure, if you will, more purified organic compounds, where it's mostly carbon and hydrogen. In other words, it starts to move from organic compounds of various varieties into what we call hydrocarbons, or substances that just have hydrogen and carbon, and that gets more and more refined as we move on. If enough time goes by, eventually that peat, which becomes buried peat, becomes coal, can actually be converted into oil, like crude oil, which we can use to make gasoline and all kinds of petroleum products. And so all of our fossil fuels, here's an oil field, they're burning the oil field as it comes out here. So all these oil fields are basically old peat bogs or swamps, which are millions of years old, which then got buried and now have become deserts after, lots of geologic changes in this area. But that carbon is trapped well underground, and it stays there. And now humans are, of course, digging it out, burning it. So there's a huge flux of carbon from deep underground up into the atmosphere, which is completely unnatural and completely unprecedented. And this is why scientists are concerned about climate change as a result. I've been throwing this term around, carbon flux, and we're just going to focus on it a little bit more before we wrap up. Carbon flux, again, was the movement of carbon from sink to sink. If we go back to this image for just a second, here's carbon flux. Now, carbon flux can be natural, like photosynthesis, or cellular respiration, decomposition, volcanic eruptions. All these things can naturally move carbon from sink to sink. So this flux can be natural. What we're seeing now is what's referred to as anthropogenic flux. That's human-caused carbon flux, and that's by burning fossil fuels. This is a very new development on our biosphere, on the Earth, and many organisms are not equipped to adapt to these very fast changes. And so we have to take the anthropogenic carbon flux seriously, because it is causing serious damage to the biosphere, to the whole planet. In fact, we have the rest of the year will be dedicated to the effects of this anthropogenic carbon flux, CO2 and the greenhouse effect and climate change. So wrapping up, here's another quick look at carbon flux. We've got natural flux, atmosphere, ocean, natural flux, primary production, respiration, anthropogenic flux, movement of burned fossil fuels back to the atmosphere. And so that is all I have for you for carbon cycling. Your homework this week is to review the very easy concepts of carbon cycling, what we call the carbon cycle, where you need to look at all of the individual processes that move carbon around. Basic stuff like photosynthesis, decomposition, waste, cell respiration. And that's all for this week. I hope you guys have a great week. Feel free to reach out for questions or issues and check in on Teams as your class rolls around. Take care. Miss you guys. See you soon.